Okay. And I believe we are recording. So, yeah. So just quick introduction. Hi, I'm Ness. I'm a second year computer science student, and I'm one of the A67 course representatives. And this is Lucas. I'm sure you all know Lucas. He's your wonderful TA. So yeah, let's go ahead and dive right in. So our first question is a simple induction question. How this is going to work is we're going to give you all about 15 minutes to work on it, and then we're going to reconvene. So in this case, we're going to be proving that for all natural numbers n, 7 to the n minus 5 to the n is an even number. So yeah, it's about, let's see, what time is it? Sorry. It is 6:22. So let's all come back at 6:37. Oh, and one thing that I forgot to mention is that Lucas is going to be in the chat answering questions. So if you have a question, feel free to put it in the chat or to turn on your microphone. We'd love to hear from you. All right, just a heads up for everyone, in 2 minutes, we're gonna reconvene and take the answer up. So. All right, so I hope everybody was able to make some progress on that question. So let's jump right in. Oh my gosh, no PowerPoint help. All right, there we go. So the first thing that we're going to do, which is always going to be the first thing we do in any induction proof, is we're going to rewrite this as a preposition. So we're going to define our P of n as 7 to the n minus 5 to the n is even. And another way to say this is that it's equal to 2 times some integer. And I'm sure you've all seen that before. Now what we want to show is that P of n then is true for all of our natural numbers. So now that we've defined that, we're going to start on our base cases. This one's pretty easy. So in this case, our natural numbers are going to be starting at 0. And we can see that 7 to the 0 minus 5 to the 0 is just 1 minus 1, which is 0, which is even. So works for P of 0. Great. Let's see if it holds for all the other natural numbers. First thing we're going to do is we're going to assume that this holds for some P of k. In other words, 7 to the k minus 5 to the k is even. And what we want to show is that if that's true, then it must be true for k plus 1. 7 to the k plus 1 minus 5 to the k plus 1 is even. So the first thing we're going to do is we're just going to assert that, right? If it's even, then it's going to be equal to 2 times some natural number. Perfect. And that's going to be our induction hypothesis. So that's what we're assuming. Now we need this to be true for 7 to the k plus 1 minus 5 to the k plus 1. And what we really want to do here is we want to make this look like our induction hypothesis. We want to have some 7 to the k minus 5 to the k term in our equation, which means we can invoke that induction hypothesis and hopefully get some results. So what we're going to do is just break this down first and foremost into 7 times 7 to the k minus 5 times 5 to the k. And this next step, we might notice that these two terms are still kind of separate from each other. We have 7 to the k over here and 5 to the k over here, not compatible. So what we really would like to do is we'd like to factor out some term. And if we look at 7 times 7 to the k, we can notice that that's equal to 5 times 7 to the k plus 2 times 7 to the k. And what that means is, and what we're doing in line 7 is we're just factoring out that 5 from our first term. So you might notice that if we expand this out, we get 5 times 7 to the k plus 2 times 7 to the k gives us 7 times 7 to the k. And now that we've factored that out, that's great news for us, right? Because now, would you look at that, we have this lovely 7 to the k minus 5 to the k term just chilling in the middle of our line 7, which means we know something about that term. We know that that is even. And so by our induction hypothesis, we can go ahead and replace that with our term from earlier. And so if we look at the two terms in this equation, by our induction hypothesis, we know that the first term is even, because anything times an even number is even. And because the second one is 2 times 7 to the k, we know that that's even as well. So we know that their sum must be even, which is exactly what we wanted to prove. So we can go ahead and show that just by factoring this 2 out front here. And what do we get? We get that 7 to the k plus 1 minus 5 to the k plus 1 is equal to some natural number times 2, which is our definition of even. So that's the meat of our proof. So what we've basically shown here is that p of k plus 1 holds if we assume that p of k is true, which is our second big chunk of an induction proof. So with that, we know that this is true, and can write that out more formally in this step. And so by simple induction, we know that this must hold for all natural numbers. Any questions? And yeah, put those in the chat or feel free to open up your microphone. Okay. I don't see any questions. If you still have questions about that one, then feel free to still post them. But in the meantime, we're going to move on to our next question. And that would be, oh, restatement. All right. So we have question 2. And I know the notation's a little bit dense. What helped me was to go and put brackets around all of those terms so you make sure you know what's happening. But basically, we want to prove that for all n in the natural numbers, if we do, you know, the sum of from 1 to n of like I plus 1 times 2 to the I, we ultimately get n times 2 to the n plus 1. So yes, again, we have, it is 6:43 at the moment. So I think we're gonna reconvene I can't do math. 6:58. Yes, there we go. All right, so we'll see you then. All right, just a heads up, everyone. This is your 2-minute warning. 2 minutes. All right, so let's get started. So, as always, you guys know the drill, this induction proof. So note that in this case, our universe of discourse is just the positive integers. So that's a natural number starting from 1, not from 0. So that's just going to be important when we're defining our base cases, and we'll get to that later. As always, we're going to start by defining our P of n. And in this case, we're going to define it as this equation at the top here. And this is where we see how useful these, propositional statements are, right? Because I don't know about you, I don't want to say about that entire equation out loud. So I know they're a little bit tedious to write in the beginning. It's going to save you so much work as you write. So yeah, we can see some applications of P here. And now that we've done that, we can go ahead and do our base case. So again, remember that we are starting from 1 here. So our base case, we're going to be looking at P of 1 and not P of 0. So this is a bit of a typo. So if we just sub P of 1, or if we just sub 1 into our equation here, we see that 2 times 2 to the 1 is equal to 4, which is 1 times 2 to the 2, which is 1 times 2 to the 1 plus 1, which, as you can see, is exactly our n times 2 to the n plus 1 form that we're looking for. So we know our base case is true. Awesome. So with that, we can go ahead and look at our induction hypothesis. So, as usual, we're going to take any arbitrary k, any natural number, right? And we want to show that if P of k holds, then P of k plus 1 holds. So line 3 plus line 6 basically is what we want. So we're just going to write out our P of k here. And now let's just examine what happens if we sub k plus 1 into this equation. We get this nice long term on line 5. And what we notice about line 5 is last question, we had to rearrange a little bit. We had to do a little bit of algebra to get the term that we wanted. Here, we have our equation for P of k. It's just staring us right in the face. No algebra needed, no rearranging. So we can go ahead. So this is just everything plus k plus 2 times 2 to the k plus 1. So we can go ahead, invoke our induction hypothesis right away, and just we get this much simpler looking equation line on the sort of the second line of line 5. And now our ultimate goal is we want this to look like what would happen if we subbed k plus 1 into this equation here. So we want this on line 2 of line 5, we want it to look like just above line 6, right? So it's just a matter of doing some algebra to make it look like that. So the first thing we're going to do is we're just going to expand out this k plus 2 term. And when we do that, what you might notice is we get k times 2 to the k plus 1 plus k times 2 to the k plus 1. So those terms are the same. So we can just say that's equal to 2 times k times 2 to the k plus 1, which is perfect, because what that actually gives us is this sort of second to last equation here, right? K times 2 to the k plus 2 plus 2 to the k plus 2. And why that's good is we can factor out that 2 to the k plus 2 and get our final equation here, which is in the form that we want it in. So, no fancy tricks here. We just did a little bit of algebra and we got the result that we wanted. And so we can see from this long equality here that we have exactly p of k plus 1, which is what we want. Yeah. So in the end, because we suppose that p of k, we can show that p of k implies p of k plus 1. We've proven our base cases. We've proven this like arbitrary implication. So by induction, again, we've proven that this holds for all numbers or all natural numbers greater than or equal to 1, all positive integers. So that's the proof. Any more questions? Okay. Don't see anything in the chat. As always, feel free to put any questions that do come up into the chat. We can answer them there. So with that, we are going to take a short 10-minute break. So we're going to come back at 10:13, and then we will move on to our next question. So yeah, 10-minute break. Get up, drink some water, do some stretches, get the blood flowing. I know it's tedious. It's good for you. And I'll see you then. All right. Hello, everyone. Welcome back. It is 7:13. I hope everyone had a great break. Um, and so we're just going to dive right into our next question here. So we've got this lovely little recursive function, where h of n is defined in terms of h of n minus 1, h of n minus 2, h of n minus 3. And we, have this, and we want to prove that h of 2n is always equal to h of 2n minus 1 is equal to n. And just a word before we start. So I know it says right up top here, question 3, strong induction, right? But you won't always have that information on an exam, right? You won't know what proof technique to use. But one, easy tip is that if you see a question where you have this function that's defined in terms of functions of like smaller numbers, then that's like 99% of the time that's going to be a strong induction question, because you're going to want to make use of this h of n minus 1 and your h of n minus 2 and your h of n minus 3. So if you can use those definitions using strong induction, that's going to be what's going to set you up for success. So yeah, we'll give you again 15 minutes. So let's come back at 7:30 and we will take it up. Also just a note, so I got a question about going back to the answers from part 1. So currently I'd like to leave this question up so that everybody can see it. But just so everybody has a reference, we will be, I think, Lucas, you can confirm this or deny this, but I'm pretty sure we will be posting these slides in the AMACSS Discord after this review session is done. So once that's done, you can go back and review all the answers there at your own pace. I hope that answers your question. All right, just heads up, everyone. 2-minute warning. All right. All right, let's do this. Okay. So, as you can see, we have our PowerPoint. All right, cool. So you know the drill at this point. You're probably very tired of me saying it. We're going to define our P of n as the thing that we want to prove for all our natural numbers. In this case, that h of 2n is equal to the h of 2n minus 1 is equal to n. And yeah, so since this is a strong induction proof, we're gonna have to be just a little bit more careful with how we set this up, right? So, you know, the first thing we're going to do is our induction hypothesis, right? We want to show that in this case, this is true for all natural numbers less than k, right? Previously, we just wanted to show that it was just true for the natural number like 1 less than k, and now we want that the whole range, right? And we're going to use that to show that k is true. But we have to be a little bit careful here, right? Because we can't just, because if that's true, then it's true for 0, it's true for 1, and it's true for 2. And you might notice that in this function here, they're specially defined, right? We can't just state them in terms of h of some other number, right? We can't say that like h of 0 is equal to like h of -1 plus h of -2. That doesn't make sense. That's not defined. So in our base cases, we need to make sure that we're proving it for 1 and 2 as well. So we can get that result just by plugging 1 and 2 into our function and comparing them with our P of n, which is what we're trying to prove. And again, the algebra is very straightforward. Just make sure that you're comfortable with doing this sort of thing. So I'm just gonna stay there for a minute longer, just so everyone gets the general idea down. And then once we do that, we are going to move in to our inductive step. All right, cool. So inductive step. So we're gonna let k be an arbitrary number, again, greater than 2 this time. So we can make sure that we're defining it in this recursive way, which is how we're gonna get our results. So the first thing, you all probably saw the hint that said we're going to split this into 2 parts, right? Because we had this 3-step equality, right? We wanted to prove that h of 2n equals k and h of 2n minus 1 equals k. So let's start with h of 2n minus 1, sorry, h of 2k minus 1 equals k. Let's start with 2k minus 1, and you'll see why we did that in just a minute. And the first thing we're going to do is we're just gonna plug this into our equation, and we're going to just expand this out. So we get 2k minus 2 plus 2k minus 3 minus 2k minus 4. And at this point, we notice if we just look at all these terms on line 16, we notice that it's easy enough to factor out this 2 from them. And the reason why that's important is we want to make this look like our induction hypothesis, right? So if we look at, for example, this first term, h of 2k minus 1 is equal to h of 2 times k minus 1. And since k minus 1 is less than k, that means that it's covered under our induction hypothesis cases, right? And what do we know about h of 2 times any number that's less than k? Well, it's equal to that number. So we get that h of 2 times k minus 1 is just equal to k minus 1 by our induction hypothesis. So very, very similar logic applies to our next term, right? We have our 2k minus 3, and we can just separate that 3 into, 2k minus 2 minus 1 and factor out the 2 from the first two terms. And again, now we get 2 times rule minus 1. And again, induction hypothesis, that's just equal to rule, our little number there. And again, that's going to be k minus 1. Perfect. So we know that this whole term here is just going to be k minus 1. And then same logic for this last term here. I'm not going to go over it because you guys get the drill. Factor it out, apply the logic. And so if we just take that, and you can see the logic expanded here, we can just take this and we can plump those new terms into our whole right side of the equation, like totally rewrite it. And so we get h of 2k minus 1 is k minus 1 plus k minus 1 minus k minus 2. And if you expand and you cancel, then you just get k, which is perfect. That's the result that we're looking for. So we've proven that this holds. We know that h of 2k minus 1 is equal to k. Now for the second thing that we're trying to prove, we know 2k minus 1, now we want 2k. So very similar deal, right? We're just going to plug this h of 2k into our equation and we're going to expand it out. And let's look at these two terms here, h of 2k minus 1 and h of 2k minus 3. So we've just done this, right? Exact same logic applies, and we can just again replace this by induction hypothesis with k minus 1 and k minus 1. Plug that into the right half of our equation here. So this maps to that, this maps to that. And we get h of 2k is h of 2k minus 1 plus k minus 1 minus k plus 1. And what you notice is that those all cancel very nicely. That's just equal to 0. And so we get h of 2k is equal to h of 2k minus 1. And you might notice that we calculated 2k minus 1 earlier. That's just equal to k. So that gives us our, our threefold equality that we were looking for. And you might notice that that is also the definition of our p of k that we were trying to prove. So, jumping back, our induction hypothesis, we supposed that it was true for all natural numbers less than k. We used that to show that, therefore, if that's true, pk must be true. And so that's all our ingredients that we need for our strong induction proof, right? We have this implication over here. And so by strong induction, that's got to hold for all, or we have our implication, we have our base cases, and so that must be true for all natural numbers. So I know that we have a lot of steps. So again, we're just going to sit here and ask and leave the floor open for any questions or clarifications. And you feel free to direct message me or Lucas if you feel more comfortable, but also feel free to share your question publicly in the chat, as we might have other people who are asking those questions or who want to know. But I did get one that's asking, why are we proving that h of 2k minus 1 is equal to k? And the reason for that is that if we go back here, we see this is our original thing. This is what we were actually trying to prove. Oh my God, PowerPoint. There we go. Nope. There we go. So we have this right here. you know, we want to show that for all n equals all n in the natural numbers, we want to show that h of 2n minus 1 is equal to n. So that's one of the things that we're trying to prove. So that's why we're concerned with it. Um, so another one that I see, this time to everyone, thank you, is why we have two cases for 1 and 2, right? Okay, so let's say that we tried to prove this the conventional way, right? Let's just assert that it's true for, or we'll assume that it's true for all less than k. Let's say we wanted to prove that it was true for like h of 1, right? And let's say we actually wanted to do this using induction. If we tried to apply our induction step to this, right? We would say, well, normal, like if we tried to prove that it was true for h for p of 1 using our usual induction logic, if you look at our induction step right here, let's say we're not supposing k is greater than 2. Let's suppose we're getting rid of that. Then we don't actually know that this is true, right? Because this whole expansion here, this only holds when n is greater than 2. The logic doesn't work if n is greater, if n is 1 or n is 2, right? So we need to have special cases for these because they're defined specially in the function. Yeah. And I'm just gonna skip ahead to this whole slide. I know different people have been asking to see different slides, so this is the whole solution written out. So hopefully that should help. Um, okay, so someone else is asking, can we use two cases? K is less than or equal to 2. So like not really, right? Because we still need to prove that this sort of holds we still need to prove that this kind of holds individually for n is equal to 0, n is equal to 1, and n is equal to 2. Those all have their own like special definitions. We don't have some universal thing that holds about them, you know? H of 0 is 0, and that's how it's defined. H of 1 is 1, H of 2 is 1, that's how it's defined. So we can't really apply any sort of general logic to them, so we need to have special cases for all of those. Yeah, okay, we have another question, this one directly to me. Just a reminder, just, if you have a question that's not like, personal, please share it with everyone just so that, other people might have that question too and want to hear the answers. So we have a question that's how are we defining P of n? And if we look back, oh, I see that's not defined on this slide. So P of n is always going to be what we want to prove. What equation do we want to be true for any value of n that we sub into it? And in this case, what we're trying to prove, PowerPoint cooperates. And again, let's look at what we're trying to prove here. we have h of 2n is equal to h of 2n minus 1 is equal to n. And you might notice this is an equation involving n, right? We could plug any value of n into here and see whether that was true or not. So we're going to let that whole thing be our little function p of n. And so saying that p of k is true is just the same as saying that h of 2k is equal to h of 2k minus 1 is equal to k, right? And if we say that, okay, well, if we want to prove that p of k is true for all natural numbers, that means that any value that you plug into this function here is going to give you a true result. This equation is going to return true for all of you who like thinking about it in CS terms. So yeah, p of n is just, what are we trying to prove? It's a little shorthand that makes our life easier so we don't have to write this entire equation out every single time by hand. Okay. All right. So I don't see any other questions at the moment. So we're still gonna have a bit of time for questions afterwards, but for now, on behalf of everybody at AMACSS, we would absolutely love and appreciate you if you filled out this feedback form, because we are always trying to make these things better for all of you and make sure that all of you have the best possible understanding you can before the test. So please fill out the form. Tell us how we did, what you liked, what you think we could improve on. And yeah, really appreciate it. With that, I think I'm going to stop recording.